All right. And so now I want to talk about algorithms that are less than n. Okay. And what does that look like? What does it look like? So if you graph how n, if we increase in O of n, we're increasing linearly. Okay. If it's n squared, it's more like a parabola. If it's n cubed, it's even. So O of n cubed, O of n squared, O of n. All right, and we have this space down here. What's in this space? Okay. Well, one of the things is, let's say that this is a stupid algorithm, okay, but it is legitimate. Okay. Let's say I already have an array in sorted order. Okay, this array is in sorted order, and I want to find the lowest value of this array. Okay, and it's sorted in ascending order. So it's sorted in ascending order. Okay. Well, my algorithm to find the lowest value of this array will be to grab the zeroth element, right? So we could just say, if this array is A, we could say A sub 0. Okay? And that is the lowest element of the array. Okay? So we just grab A sub 0. Now, you'll notice that when n equals 5, it's A sub 0. When n equals 10, it's A. We just do this one step, right? When n equals 300, we're always searching through the same number of squares as n increases. It's the first square, right? We're just, no matter what, our answer is there, no matter how big our array has to be. All right? So those are constant time algorithms, right? In this case, it's a constant time of O of 1, and that's how we say it's constant time. It's not dependent on n. It actually stays constant no matter how big this array has to be. Okay, so that's an O of 1 algorithm. Okay, and no matter what, even if it's O of 15, like I have to, if my answer happens, I have to search through at least 15 squares each time, but it doesn't depend on n, right? So it's O of 15, we still call it O of 1. Okay, it's always O of 1. Then what was that? Oh, then we also have our other case, okay? And our other case we've done before is you go to a bar, and remember how we're doing the pick a number 100 game, right? And so we have sorted values from 1 to 100, and you say to them, I feel like I can pick this in 7 guesses. And they're like, you're on, Mac. That's how they talk at this bar. Mac, you know, like that kind of bar. And so you split it in half, 50, right? And then so you have 1 to 100, and I know it could be 0 to 100. I always screw this up anyways. 50, and then you go to 75 when they say higher, and then they say lower, and so you do 50 plus 75. Don't tell Frank that I used a calculator for this. I am a terrible mathematician. So it's 125 over 2, and we're at 62.5, 62.5, right? And then in about, well, let's just prove it. 62.5, and then they say higher again, and we put that over 2, and it's 68.5, and they say higher again, and then we at 75 more, 68.5. And they say higher again, and so now we keep on getting closer and closer, and in about, so 4 guesses, we've made the space go down to 10, okay? And when we get to 7 guesses, well, let's just do it. 68.5 plus, I don't know why, it's just such a pain in the you know what? You can tell it's summer. 71.75. So this is 71.75. Okay, and we've done 1, 2, 3, 4, 5 guesses. Okay, 5 guesses so far. 71.75, and our space is 4 things. If so our space is 71 to 75 now, which is 4 things, and we do this game again, and they say higher, so then our space is, so we split it in half, and we guess what, 73, and they say higher, so we're going to 74 and 75, right? And so we do 1, 2, 3, 4, 5, 6, 7 guesses. Okay, we have narrowed it down to where their number is, or what their number happens to be. Okay, and we've already guessed 75, so it has to be 74 in this case. Okay, so we had a search space of 100 things. They're sorted, and we didn't have to search through all 100 things to get to our answer. We had to search through some subsection of the 100 things. Okay, and so we can begin to think, well, maybe this is some sort of different relationship than anything we've seen before. Okay, let's talk about that. So let's do a little experiment. When n, so we have 2 things, right? So when n is 2, you're saying pick a number between 1 and 2, including 1 and 2. Okay, so it's a search space of 2, right? And the number of times you have to guess in the worst case scenario will be 2. Okay, not so good right now, right? Let's say we go up to 4, and it's sorted again, right? So pick a number between 1, 2, 3, 4, right? A search space of 4, and find out what it is. Well, you guess 2, right? And they say higher, right? You guess 3, okay, or 4, right? And then you'd know. So you could do it in 3 guesses in the worst case scenario, okay? I believe. And then if we do 8, well, 8, 1 through 8, right? Including 1 and 8. Okay, so you pick 4, they say higher. You pick 6, they say higher. You pick 7, they say higher. 4, they say higher. You pick 6, they say higher. You pick 7 or 8, it doesn't matter. They say higher in the worst case, and your worst case is 4 guesses. Okay, you can kind of see what's going on here. We're doubling the space over here, and we're not going up as fast over here. Okay, let's double it one more time. 16. Well, 16, I guess 8, they say higher. Okay, I guess 8, they say higher. 16 minus 8 is 4. I guess 12, they say higher, right? And then I guess 14. So I guess 8, 12, 14, and then 15 and 16. Okay, so I can do it in 5. All right, you kind of getting it? Let's double it again. Well, this will probably, if we're kind of looking at, if we're squinting our eyes here, you're like, well, Ashok, every time you double it, we seem to be going up 1 over here. I wasn't born yesterday, Ashok. And 64 is what? 64, 7, and then if we go one more time, it's 8. And I think that is true for it. So that's how you get the 100 thing. So if you go to 128, it's 8, right? Which means that to guess the value of 100 will take 7 guesses and some change. All right. So that's why the bar game, I can do it within 7 guesses, is fairly good. You're gonna win most of the time, most every time. Okay. And we can do this again. 64, 32, right? 32 and 64. We'll eventually get there. Okay. So we're going up by 1 each time, even though we're doubling here. Okay. Someone might look at this, some mathematician in the crowd, which I'm not. Okay. But somebody might look at this and say, Well, this is like n equals 2 to the power of number of guesses minus 1. Okay? As if to say, right, 2 to the power of number of guesses, in this case, will be 2 to the power of, so that's 2 in this case, minus 1 is 1, and that'll equal 2. Okay. And then if the number of guesses is 3, we go 2 to the power of 3 minus 1 is 2, so 2 to the power of 2 equals 4. Okay. And so you're looking at this and you're like, okay, that's an interesting relationship. How do we say what order of n that is? And a mathematician in the crowd would say, well, if I take the log base 2 of both sides, okay, I'm going to just take the log base 2. All right, I get number of guesses minus 1. All right, so and then I can say number of guesses equals log 2n minus 1. All right, and what does that mean? Well, that means our algorithm for using binary search on a sorted array, okay, is as n gets bigger, our number of guesses grows with log base 2 of n, okay? Or another way to say this is we take this and we say this algorithm is O of log n, okay? And the base doesn't matter. We just say O of log n. We just make a general thing of saying O of log n. So if you see log n, that means it's something like this. How's log go? I think it's like this. Okay? Okay, it's growing slower than O of n. It's growing faster than O of 1. Everything's growing faster than O of 1. All right? But it's going slower than O of n. All right? And so if you can get to that kind of runtime, you're feeling pretty good because it's as n increases, the number of things you have to search through doesn't increase that much, right? Where in linear search, we would be at 128 things over here. But in binary search, where we split the space in half each time, we're at 8 things. That's a huge market difference as n's going to infinity, right? Or in a place like Old Westbury, where n goes to 5,000, 10,000, right, whatever, or, you know, even bigger universities, right? We have to look through all those records. Having it sorted means we can kind of jump to the record pretty quickly. The number of things we have to search through is not growing as fast as the number of things that are in the search space. Right? So powerful stuff. So this is, just to make it clear, this is binary search of a sorted group of numbers. Yeah, I'm going to say sorted array. It's fine. That's the example. So binary search of a sorted array, as opposed to linear search of an unsorted array, right? Which was O of n. Okay? Binary search of a sorted array is got this powerful log of n thing to it. Okay? Sweet. Those are the main ones. There are other O of n's, but I'm not gonna hold you to them. So next video, let's talk about our algorithms for sorting, the 3 I showed you, and let's determine their O of n's.